So here's the boat I made. You can see it's an outrigger design, kind of a catamaran type thing. And it's really just two hulls connected by some dowels. And then it has a platform there. And so let's see if it floats. Oh yeah, beautiful, easily. Okay, now let's put some weight on there. I think I asked you for about 25 grams. So let me grab some weights here. Here's 5 grams. And here's 20 grams. Okay, you know what? That wasn't a challenge at all. So let's put a little bit more on there. Like, maybe we'll put Moana right here. And you know what? I'm so confident in this boat. I don't think 25 grams is even a challenge here. Let's kick it up to, I don't know, how about 500 grams? Something like this. Let's try it. Okay, so it's listing a little bit, but supports it perfectly. So today, our goal is to talk about buoyancy.
Well, aloha everyone. Today we're going to talk about buoyancy. Well, buoyancy obviously is the ability of an object to float in a fluid due to a buoyant force.
So what is this idea of buoyant force? Well, normally when we have an object and we put it on top of a solid surface, we say that there's a normal force that holds that object up against and acts against gravity. So because of that here, the electrons inside the rim of the bathtub are interacting with the electrons inside this plastic bottle. And because of that, it doesn't fall due to gravity. But unlike the rim of the tub, where I can't put my hand into it, I can put my hand directly into this water. So the mechanism by which buoyant forces arise is totally different from that of a normal force. If I take this bottle and I place it here, you'll notice that it sinks a little bit into the water. Not a lot, but a little bit. And because of that, it's having to push water out of the way. There's another thing you might notice when we put that in, but you have to watch carefully. And to demonstrate, watch this level right here along the edge as I submerge this further. It's pretty subtle, but did you notice that the level of the water rose? Okay, this is a big container. Maybe we should try it in a smaller one. So in essence, when this bottle pushes the water out of the way, it's having to hold that water up against gravity. Gravity's also pulling on this bottle downward, and so the two of them reach equilibrium. You'll notice one more thing. The more water you push out of the way, the more that this object wants to rise. It takes only a little bit of force to submerge this into the water a little. But to get this thing completely submerged takes quite a bit more. In fact, once it's quite all the way submerged, if I let this thing go, it pops up quite violently because of the amount of force that is acting on it, the amount of buoyant force. And the buoyant force depends, obviously, the first thing is, on how much water it pushes out of the way. The buoyant force depends on the volume of water displaced. Now, it turns out the fluid here might not always be water. We might have something like syrup, or honey, or milk. Or maybe we have something ridiculous like liquid mercury. In those types of different liquids, the buoyant force is going to be different. And this object will float at different levels due to the fact that these fluids have a greater density or a smaller density. If we put this in, I don't know, a whole bunch of rubbing alcohol. So because of that, when we have this object floating, it depends on, first of all, the volume that it's pushing out of the way. Second of all, it depends on the density of the fluid. The final piece that the buoyant force depends on is gravity. Because you can think of it, remember, when you push this down into the water, you're having to hold that water up against gravity. So, the weight of the fluid that you pushed out of the way, the weight of the fluid displaced, is going to be the buoyant force.
So what's the formula for buoyant force? Well, we remember from earlier that it was the weight of the fluid displaced. So, the buoyant force, Fb, is equal to the force of gravity on the fluid displaced. Okay, well, how do you find the force of gravity? Well, that's easy. The force of gravity on anything is m times g, mass times the force of gravity. The problem is right here. If we push fluid out of the way, it's hard to tell what the actual mass is unless we fill something up to like where it overflows and then capture it all. So instead of talking about mass, usually we talk about density. Now in physics, we're going to use the letter rho for density. Rho is density. So that's the Greek letter rho. And it's going to stand for density. And you may remember from chemistry that density is equal to mass over volume. So I can solve this for mass, and I can get mass is equal to rho times V, where V is volume. Okay, so the buoyant force is equal to rho times V. We're going to substitute that in from our mass, times G. Rho V G. This is how you find the weight of the fluid displaced. And you can calculate what volume needs to be displaced in order to make anything float.
There's a common misconception out there that buoyant force doesn't affect heavy objects, objects that don't float. And it turns out it does. It's just a little bit harder to see. So I have here a spring scale. Now I'm going to hold this 1 kilogram weight on, not like that. Now there's a common misconception out there that buoyant force doesn't affect objects that are heavy, large, solid objects like this 1 kilogram weight. But in fact, it does. It's just its effect is a little bit more subtle, and it takes a little bit more careful experiment in order to see it. So, check it out here. I have a spring scale, and I'm going to lift this weight. It's attached using a piece of fishing line. I'm just going to hold it out here, and it turns out we're getting a pretty consistent, this is a 1 kilogram weight, and we're getting pretty consistently just below 10 newtons of force due to gravity. Okay, so now I'm going to slowly submerge this into the water. And when it's like this, it's much closer to 8 newtons. So 2 newtons isn't enough to make this float, but it is enough to make a difference in some cases.
So, how big of a boat would I need to put my 1 kilogram mass in order for it to float? So here's 1 kilogram. And how big of a boat and how much volume would I need to displace in order for this 1 kilogram weight to just barely float. What would I need to do? Well, I know that in this case we have some forces that must be in equilibrium. Gravity is trying to sink the boat constantly, Fg. And pushing back on this is the buoyant force, Fb. So we know that if that boat is just barely going to be sitting right there at the edge, and any little wave will kick water into it, but as low in the water as it possibly can, we know that the force of gravity must be equal to the buoyant force. All right, the force of gravity on the mass is m of the mass times g. That's equal to the buoyant force is rho v g. But remember, rho is not the density of the object. This is the density of the fluid. In this case, it's water. V is going to be the volume displaced, and thus it's going to be how big my boat needs to be, and G is going to be gravity. Now you may see something already here. You may notice that this G and that G are the same thing. So it turns out the size of this boat is not affected by how much gravity you have. A boat on Mars would float exactly the same as a boat on Earth, assuming they had the same sort of oceans we did, and assuming the density of the water was the same. Okay, so M is equal to, M for the mass, is equal to rho of the fluid times V of the fluid. So we're looking for how big of a boat we need. So we need to solve this for V. So V is equal to M over rho of the fluid. This is M of the mass. Okay, this is equal to, well, the mass is 1 kilogram divided by the density of the fluid. Well, what's the density of this fluid? Assuming we're trying to float this in water, the density of pure water, you may remember from chemistry that the density, they probably used a capital D for water, was 1. 1 what? 1 gram per milliliter. Or maybe they called it 1 gram per cubic centimeter. But in physics, we don't like to use grams and centimeters. We like to use kilograms and cubic meters. So the density of water, by definition, is 1,000 kilograms per cubic meter. So you can think of this as saying a 1 meter by 1 meter by 1 meter cube tank filled with water to the brim would weigh 1,000 kilograms. Okay, so now that we have this, we can say, oh, well, this is pretty simple. Kilograms on top gets rid of kilograms on the bottom. We're left with 1 over meters cubed, which is just cubic meters. And it's 1/1000th of a cubic meter, or maybe it's 0.001 meters cubed. So that would need to be the minimum volume of my boat in order to keep this object from sinking. In order to make my 1 kilogram weight float, it would need to be in a boat with at least that amount of displacement of fluid. Okay, so let's try another example. Let's imagine we have a piece of metal, and this metal happens to be aluminum. And this metal is, let's make it 1 meter by 1 meter by 2 meters. So we have a sort of rectangular prism of aluminum here. Maybe I can draw it a little bit better. Something like this. Okay, so that rectangular prism, let me label that a little bit better too. So 1 meter, and 2 meters along that edge. Okay, so we have this piece of aluminum, and the density of aluminum is somewhere around 2,710 kilograms per cubic meter. So I want to know first, what is the weight of this block? So 1, what is the weight of this block? And 2, I want to know what will the reading on a scale be when submerged in, let's not use regular water, let's use ocean water. And I'm not talking about that drink from the one place. I'm talking about the actual water from the ocean, the salt water. Because it has salts dissolved in it, the density of the water for the ocean, salt water, for the ocean, it's a lot closer to 1,025 or so kilograms per cubic meter. And I want to know the answer to these two questions. First, what is the weight of this block? That's what the scale will read when you're holding it out of the water. And then when you lower it down into the ocean water, what will the weight of the block appear to be? It won't actually be that, but it will appear to be lighter because of the buoyant force acting on it. So, what should the weight of this block be underwater? Well, let's solve part 1 first. The first thing we need to do is we need to determine this thing's volume. So, the volume of this object is going to be length times width times height, right? Which is, the length is 2 meters, the width is 1 meter, and the height is 1 meter. So this is going to be 2 cubic meters is our volume. The next thing we need to do is we need to plug this into the density formula to find the mass. So density is equal to mass over volume. So mass is equal to density times volume. That's equal to, we're going to use, since we're trying to find the mass of the aluminum block, we're going to use the density of aluminum, 2,710 kilograms per cubic meter. Times our volume that we just found was 2 cubic meters. So this is going to be equal to, let's see here, 0, 2, 4, would be 4, so 5. And then meters cubed here, meters cubed there, we get kilograms. So, outside of the water, the mass is 5,420 kilograms. But we're not done yet. We're not looking for mass, we're looking for weight. And remember, weight is the force of gravity on something. So the force of gravity is equal to m times g. This is equal to 5,420 kilograms times 9.81 meters per second per second. This is going to be equal to 53,170.2 newtons. And this is what the reading will be when it's outside of the water. However, when I lower it down into the water, there's going to be another force, which is going to cancel some of that weight, and it's going to make it feel like it's lighter, the buoyant force. So in order to figure out what the scale is going to read when it's in the water, I need to figure out what the buoyant force is. So FB equals rho V G. That's equal to, in this case, it was 1,025 kilograms times a volume of 2 cubic meters. That's kilograms per cubic meter. And times gravity is 9.81 meters per second. This is equal to 20,110.5. Let's see, meters cubed there, meters cubed there. We have kilograms times meters per second, which is a Newton. So 20,110.5 newtons is going to be our buoyant force. When this happens, it's going to act as if it's trying to cancel some of the force of gravity. So because of that, the reading on the scale reading, will be 53,170.2 newtons minus 20,110.5 newtons, which is equal to 33,059.7 newtons. So it turns out that piece of aluminum feels a lot lighter when you're in the water and a lot heavier when you're out of the water. If you've ever been fishing, you probably noticed this. The fish, okay, yeah, when they're in the water, they can kind of struggle a little bit, and you have to kind of pull them out. But when is your line most likely to break? Right as you're about to pull that fish out of the water. As he starts coming out of the water, all of a sudden, he feels a lot heavier. And the line will, if it's going to break, it will break probably then. So that's really all there is to it as far as buoyant force goes. So, yeah, there's a lot of geometry that's going to be involved, and there's going to be a little bit of review of density that you need to remember. But otherwise, that's about it. So, mahalo for watching, and see you next time.